Okay. So hello, everyone. Uh, so today is the second helping discussion session uh, for this course of Geometry of Vision. So today I will be discussing a few problems um, from the second week. Okay. So just to remind you, uh, I can give you my introduction again. Yeah. So I'm Prerak from Aizer Bhopal, and I'm conducting this weekly discussion session with you guys. And this is our second live discussion session. And the recording of this discussion session will be uploaded on the YouTube channel. You can search on in your YouTube NPTEL Geometry of Vision in brackets Prerak. You will find out my channel where I will upload this today's session as well, and I have uploaded the previous session also on that same YouTube channel. Okay, so I hope um, Tamil Arasi, I am audible as well as you can see the screen. Yes, so you have raised your hand. Do you have any query? Or you are just saying that you can unmute yourself and say. If you are not able to unmute, you can just write it in chat box also if you have any difficulty. So this is not that formal session we are having. Okay, moving on. So this is the course website. Yeah. So this is the course website that um, I'm following. This is Professor Vijay's ex website on this course. Okay. And here are four drawing challenges. So in week two, there was one drawing challenge, which I've also uploaded this link of the drawing challenge. So you need to draw, you need to take printout of that, and then you need to draw this. You need to complete the figure in some sense, and then you need to upload it on in the Padlet. That's the whole idea of these drawing challenges. So there are four drawing challenges, and in order to complete this course, these drawing challenges are required. They are necessary step in order to complete the course. Yes. So welcome everyone who has joined later. Yeah. So this course website and the links to drawing challenges. Actually, this whole presentation I will upload uh, in the web, and the link to that presentation I will share in the YouTube in this YouTube channel which is highlighted. So you can search this. You can search for this channel in your YouTube, and you will find out I've already uploaded the first discussion session. You will be also able to find out the second live discussion session on this YouTube channel, and the description you will be able to find out this slide of the that I'm using today. Um, yeah. Now let's move on to discuss some question. Okay. Yes. It's time to discuss some questions. Okay. So you can see. So here is an answer also to that question as well as increase brightness bit. Yeah. So I think all of you can see the slides. If not, um, you can just unmute yourself and ask for it. Okay. So the first question that you can see on your slide is imagine three sets of railway tracks, no two of which are parallel, as in the following diagram. So we have three railway tracks in the ground plane, and we have this. So this is our projection plane. Okay, and you are looking from here. So this is you. Now the question is, how these remaining two railway tracks will appear in the projection plane. Okay. So can anyone tell me why? First of all, you can see the answer as well. So I'm not gonna say it loud, but we let's look out for the justification for this answer. So as you can see, there are three vanishing point, correct? So we have three vanishing points. So first question is, why are there three vanishing points? Okay. Uh, why three vanishing point? Why are there three vanishing points? Okay. Why not lesser or more than three? So can anyone answer this? Yes, Kamalji.
because these railway tracks are not parallel.
Correct. So you are using a fact that parallel lines in the ground plane converges to the same vanishing point, correct? And if two lines are not parallel, then they must converge to different vanishing point, correct? That's what you are using here. So is everyone able to follow this explanation of vanishing point? And the answer is, let me write it in different color, non-parallel lines. Okay, so that's the explanation for this. Okay, so now let's move on to the next question. So, so bear with me. Everywhere, so wherever I've written E2, it's P2 actually. Okay, so yeah. So the question is, if a line in P2 contains two planes at infinity, then the line must be L infinity, which is the line at infinity. Okay, is the question clear to all of you? So the question says, if a line in P2 contains 2 points at infinity, okay, then this line must be L infinity, which is the line at infinity. So this line of infinity is a line that has each point is a vanishing point for some line in R2. Okay, so P2 is nothing but R2 union L infinity, in other words. Okay, so this answer is true, as you can see, but can any one of you give an possible explanation for this, why this is true? So let us look at the hypothesis that we have in this question. So we have this hypothesis that uh, so a line in P2 contains 2 points at infinity. Okay, so there is a line in P2 which contains 2 points. Okay, 2 points at infinity. That means, what do we mean by points at infinity? So they must be vanishing points of some line in R2, correct? And these two lines must be non-parallel to each other. That's also this that should be the case. Otherwise, if L1 and L2 are parallel to each other, then the A must be equal to B. So they are two distinct points. Okay, that's the assumption. Now, why? So the only thing that you need to argue here is that why that line, this line L, can't lie inside R2. Okay, if it's not line in R2, then only it's the line at infinity. Okay, because P2 is what? P2 is R2 union L infinity. So if the line is not lying inside R2, then it is in L infinity. Okay, then it is L infinity only. So the simple answer here is that because it contains 2 points at infinity. Okay, so can you draw a line? So now the question is, draw or can you draw a line in R2 with 2 points at infinity. So is it so? Can you draw a line in R2 which has 2 points of infinity? So first of all, if I am talking about lines in R2, if I'm talking about lines in R2, okay, so it meets infinity, it meets L infinity at the end points, okay, and it meets to the same point. It goes to the same point. This end this end goes to the same point. This end also goes to the same point. Correct? At L infinity. So a line only intersects L infinity at a unique point, okay, which is determined by this line. So let's call this line to be some M, and the point determined by this line or the class of this line in L infinity. So it intersects, so M intersects L infinity at point, this point, okay. So this line, so there is no line. So the answer to this is there is no line in R2 which has more than 1 point at infinity. Okay, with 2 points at infinity. Okay, so there is no line in R2. So that means if I'm talking about any line in P2 which has 2 points at infinity, then that line has to be L infinity. Okay, is it clear to everyone? Okay, now let's move on to the next question. So in the next question, we have again, this is P2. So every line in P2 that is not line at infinity meets exactly 2 points at infinity. So every line in R in P2 that is not that is not the line at infinity. Okay. So in this, just look at this phrase of the sentence. So in this sentence, I am looking I am looking at lines which is in R2 only. Correct? Okay. So I'm looking lines in R2. I'm only looking lines in R2. Okay. And now now reads the later half of the question, which is meets exactly 2 points at infinity. So and now we know that any two lines in R2, okay, intersects only a single um, okay, sorry. Yeah, so it says that every line in P2. So I'm only taking one line, and now we know that that line is lying inside R2 because it's not the line at infinity. Okay, so P2 is, again, let's recall, is nothing but L R2 union L infinity. So this line is not L infinity that is given to you. Okay, that is what that phrase means. So the line in consideration is in R2. And we know any line in R2 intersects L infinity at at only a single point. Okay, and that point is precisely determined by that line. So that's why this statement is false, because it's exactly at one point. Okay, then it will be true. So that's why this statement is false. Everyone fine with the explanation? Any doubt? Okay. Now let's discuss another question of the same flavor. Okay. So now I will leave this. So I will ask you for the explanation for this question. So every ordinary line in E2 meets the line at infinity somewhere. So this question is very simple. That if I take any line in E2, sorry, P2 basically, if I take any line in P2, then it meets the line at infinity somewhere. Is it? So the answer is true, but can anyone come up with an explanation to this? Anyone? The explanation is already simple. I've already uh, told you multiple times. So break this question. So the question is every ordinary line in P2. Okay. So yeah. So the question is every line in P2. So what is P2? P2 is nothing but R2 union line at infinity. Correct. So what are the lines in P2? So it's either L infinity or it's any line in R2. Okay. So now you have two sets of lines. So lines in P2 is either L infinity, okay, or um, it's a line in R2. Okay, so there are only two possibilities for any line in P2. Correct. Now, can anyone tell me now what will be why it's true? Why this statement is true? Anyone? Okay. Uh, no problem. Uh, so what does it mean by meets at line in infinity? So it says that whether there is an intersection to the line at infinity. And what is line at infinity? It is nothing but L infinity. Correct. So if I take L infinity, so L infinity intersects to L infinity because it's the same line. So the intersection will be at each point. Correct. So now if I take any line which is in R2, so if I take any line which is in R2, so if I take any line which is in R2, correct? So it will intersect the line of infinity, which is the L infinity, where at the end points of this line, L, okay? Because that's how we define L infinity. How do we define L infinity? L infinity is nothing but point determined by the class of L, where L is a line in R2, okay? So, for example, this line, so in this case, L will intersect L infinity at precisely this point. So every line, so if you take any line in P2, it will intersects, it will meet L infinity somewhere. Okay. So that's why it's true. Okay, now let's discuss this question 23rd question. This um, in this question and the question that follow, we will explore the shape of extended Euclidean plane, which is P2, by examining how simple construction with points and line divides up the plane. Okay. So let L be a line in E2. How many pieces will L divide E2? So P2, just read P2 it out. It is P2. Okay. So the question is, if I take any line L in P2, how many pieces will this line L divides P2? Any guesses? Any guesses?
I think one piece.
One piece. Okay. Okay. Anyone else wants to add to whatever what Kamaljeet just said? So let me take any line L in this plane. So why not? Let's take this line. Yeah. So let's take this line. This is my L. Okay. So it is going in both of the direction. And now thing is, how many pieces does this L divides into? So Kamaljeet, yeah. So you say that it will divide in just a single piece. Can you give me an explanation to that? Why do you
Sir,
think it will be just, yeah?
sir, is there any 2 points at infinity?
Sorry,
Is there 2 points of infinity?
2 points at infinity. No, but this line will determine a single point at infinity. Correct. Okay, so let me answer this. So what you guys can see in this figure, in this R2 plane. So I've drawn R2 plane only. Okay. Um, yeah. So I've drawn R2 plane only. Now in this R2 plane, you can see uh, this point, which is on the top of this line L. Let's say A. So if I and this point, which is on the bottom half of the line L, let's say B, can I join? If I can join these two points, okay, without going through L, then uh, this region and region on the top, this region must be connected to this region. Correct? Because I'm removing this line. I'm removing this line L from R2. Okay. So now if I remove this line R L in R in P2, basically I'm removing. If I remove this line P L in P2, uh, now the question is how many regions does it divide into? Okay. So if I say that if I start my journey from A, does there exist a path I can get from A to B? Okay. So you might say that it's a stupid question because we already have a path like this. Okay, but it's not the path that you need, because this l this L has been cut off, so you can't cross L. It's, think of like there is a deep uh, there is a yeah, you can't pass this L because there is nothing to walk on. Okay. So you need to say that whether can you come from A to B, and the answer is yes, you can come. And how can you come from A to B? Can anyone tell me? So let me draw a line that joins A and B. Okay. Now you might say that this line is passing line L, so isn't it the same path that you were that might, yeah. So this is the line that I'm having, but no, this is not the same path. I'm considering the path that is going in this way. So I'm going this way from L, and I'm coming from this way. And do you know how is it possible? If I go from A to the top side to the infinity end, and I will come back to B. Why? Because I will be intersecting to L infinity line. Okay, because each line in R2 determines a point in L infinity. Okay, so if I say this line is M, so what point will it be intersecting? It will be going by a point which is this point, correct? In L infinity. So I will be using the path from A to B. So that means, in other words, if I take any point which is on the top half of the L, and any point which is in the bottom half of L, I can always find out a line which join these 2 points. Okay, and I will go via infinity at infinity along this line to come back to this point. Okay, so you can try it by yourself also. For example, if I give you this point, so yeah, so the reason that I'm so this is one reason that I'm interested in. and this is another reason. Okay, and I have taken 2 points, and I can walk from A to B by an infinity point at infinity. Similarly, if you give me any other point, for example this, my bad, for example this and this, call it A1 B1, I can again find out a line, and I can come back to B B1 from A1 by a point at infinity. So that means this region is connected, it's not broken. Okay, so this region, the region in the gray, is a single region, it's not two regions, it's a single region. That's why Kamaljit's answer is correct. Okay, I hope I have made sense to all of you guys. You you got some understanding. If not, you can ask questions. Okay. Now let's come back to this question. Okay. I don't think you guys are able to see this question. So let me first zoom in a bit. Yeah. So the question is, which of the following depicts the restriction of R2, this depicts the restriction to R2 of a complete triangle in E2 with exactly one ordinary point as a vertex. Okay. Uh, so you only need to find out, first you need to realize uh, that these three figures are triangle. This figure is not a triangle though. No, this figure is also a triangle. This figure will also give you a triangle. Okay. So all of three figures are giving you a triangle in P2, correct? So it's in P2 we are getting a triangle, not in R2. It's not a triangle in R2. It's triangle in P2. That's what you need to remember. Okay. So now let's come back to this. So why is it a triangle in P2? So when do we say it's a triangle? So triangle has what property? It needs to have three vertices, okay, and three edges also. So a triangle is with three vertex and three edges also, correct? So can you say that it has three edges in the first diagrams? Okay, so let's call this to be first one. So can you see it has three vertexes? Can you see three vertex in this figure? Any one of you? For a triangle, you need three vertex. Okay, can you see three vertex in this first figure? And hint is two vertex are lying in line at infinity. Okay, so two of the vertices lying in the line at infinity. Now can you see where are those two vertices? Okay, so I will not stress you more on this. So one of the vertex, let's call this line to be L1, call this line to be L2. They are not parallel, so they will intersect. So they are not parallel. That means it will have two vanishing points. Okay, so that means they will intersect at 2 points to the line at infinity. Okay, so think of that there is some line at infinity going on, which is at infinity. Okay, so you can't see this line in real life. So there is some line at infinity. So this line will also intersect this thing, this at some point, let's say some B, and this will also interact at some point A to the infinity. Okay, so you have 2 points at infinity. So these points have precise description also. Okay, so you have 2 points at infinity, and this is your third vertex C. Okay, so it has three vertex, correct? And how many edges does it have? It has three edges as well, because this BC will be the first edge, AC will be the another edge, and BA or AB will be the third edge. So it's a triangle. Okay, so it's a triangle in P2. Okay, and it is also the answer of our question, which says that with exactly one ordinary point as a vertex. So ordinary means that the point, ordinary point means the point needs to lie in R2, correct? So this point is lying inside R2. This point C, only point C is lying in R2. Other points A and B, they are at line at infinity. Okay, so that's why it's a triangle with exactly one ordinary point as a vertex. So am I clear on this? So there are two things to understand. First thing is that whether whether this first diagram is a triangle or not. Okay, that we have seen because it has three vertex and three edges, so it's a triangle. Okay, but in PT, in P2, not in not in R2. Okay, now the second question is, does it answer our question? That means, does it have exactly one vertex as an ordinary point? And the answer is yes. Only C, vertex C, is lying inside the plane R2. So only C is the ordinary vertex. Other two vertices A and B are at line at infinity. So they are. So this is the answer of our question. Okay. Now I will leave you guys to figure out whether this second figure is a triangle or not. Okay. So can anyone tell me whether this is a triangle? Let me draw the
Yes.
area that I'm telling you. So this reason, the reason that is being colored in this maroon, light maroon color, is this a triangle? Is the shaded region triangle?
Yes, it is a triangle because there is one point at infinity.
Yeah, correct. That's the correct answer. Okay, good, good, nice. So even you can see that this uh, this diagram 2 in particular, okay, divides into multiple triangles. So this blue one is also a triangle according to the first figure. Okay, this one will also be a triangle, and this one will also be a triangle. This one will also be a triangle with exactly one ordinary point as a vertex, and this one will be the triangle with exactly two ordinary points as vertices. Correct. So, so each of the region that I've drawn is a triangle, but two vertices at the critical point, three vertices, two vertices as ordinary point, one vertices as ordinary point. Okay, so yes. Okay, now let's move on to the next slide. So any questions so far? So this is where I stop for some questions. If you guys have any regarding the projective plane, then I will move ahead for the other questions that to discuss. Okay, so no question. So let's again come back to the description of triangles in P2. So I've already discussed. Yeah. So so the question is, now we already know what triangle is, so we don't need this definition to see anymore. Okay, so we all know what triangle is. I've already discussed this, so no need to go into that. Now let's come back to the question directly. So now question is it possible for a complete triangle in P2 to have no ordinary points as vertices? That means no vertex of triangle in P2 has um,
Sir,
yes,
I think there we can apply the horizon line theorem because all the vanishing points lies on them,
correct.
and answer is
So
no.
the yeah, so basically the answer is, you are saying correct. Its answer is no, and the reason is because collinear points doesn't form a triangle. Okay, so if all three vertex are going to be in line at infinity, that means all three points are collinear, and collinear points doesn't form a triangle. So that's why the answer is no. Okay, yes. And the second 25th question we have already seen, so I will not go into that. Now let's see this 27th question. Into how many pieces does a complete triangle with three ordinary vertex points divide E2? So it is saying that how many pieces does a complete triangle with three ordinary vertex? Okay, so that means you are having a triangle like this. Okay, so this is your triangle. where all 3 points ABC, all 3 points ABC are in R2, are ordinary points. Okay, so everything is lying inside R2. Okay, so now the question is, how many reasons does it divides P2? Okay, how many reason uh, it divides P2 into? Okay, so yeah, so you can see that there is one reason. Obviously, you can see this one reason, which is this triangle. Okay, now how many other reasons does it have? So again, I will do the same exercise that I did for a single line. Okay, so for example, if you take a point over here, my bad. If you take a point here, call that point A, and if you take a point here, call that B. Will that will it be possible for you to get from A to B? Okay, so for that I will draw a line joining A and B. Now, as you can see, uh, I need to cut off this line into two parts, because here also, because at this point there is a cutoff, at this point there is a problem. Okay, so I cannot go, there is no path A joining A and B via infinity, line at infinity. Okay, so that means these two reasons must be different. Okay, so what two reasons must be different? Let me just draw them. This reason must be different from this reason, the reason in the blue. Okay, good. So now let's see what about point in, yeah. So now let's see what about point A and D. Okay, so you can see point A and you can see point D. So can you draw a line? Yeah. So I can always draw a line joining these 2 points. Okay. So this is the line that joins A and D. Now can you go from A to D by a line at infinity? And the answer is yes, you can go, because there is only one problematic, there is only one hole which is at this intersection at C. Okay. So you can go. There is no other hole. So you can go by a line at infinity from A to D. Okay, so and similar, and for, if you, so in other words, more generally you can say, if you take any, if you pick any other point in this region, in the blue region, and in the region that I have not drawn anything, so yeah, in the region below AB, if you pick any 2 point, you will be able to draw a line which only has one hole. Okay, for example, in this case it has two holes, but you can see that you can join A1 and D1 by a point at infinity. Okay, between that there is no other hole coming in the picture. Okay, so in other words, you can say that these two regions must be same, these two regions must be connected. Okay, and this will go along, and the boundary of these regions will be along these lines. So along these lines, these regions will be same. Now I leave you for you guys to figure out. Uh, I will give you the answer. Reason this and reason. Okay. So reason B and reason this reason. Um, yeah, will be same. And similarly, you can guess now what else. I need to use a different color. This reason along the lines, and this region will be same. Okay. Yeah. So how many regions does it partition into? One, two, three, one, two, three, and four. It partitions into four regions. So this will be the answer. Okay. So yes. Um, yes. Any questions before we move on to our next and next part of this of today's discussion? Any question? Okay. So you guys don't have any questions, so it's fine. So harmonic conjugate. Let's move on to discuss harmonic conjugates. Okay. So how do we define harmonic conjugate? I suppose that you guys have all seen the definition, so I will directly jump into this figure. Yeah. So this question. Okay. So harmonic conjugate uh, of zero and half. So this point and this point, and one with respect to one. We need to find out the harmonic conjugate of one with respect to these 2 points. Okay. Now, what's the procedure? How do we do it? So we need to take any point which is not in this line. So let's call this line L. So we need to take any point which is not in this line. So I'm taking this point. Um, so let's take this point which has already been taken. So let's call that point to be P. Okay. So this is our A point. This is our B point. No, sorry, this is our C point, and this is our B point, and this is AC of B that I want to calculate. Okay. And now I need to pick another point on this line BP, which I am taking it to be Q. Okay. Now once I have these 2 points P and Q, idea is to join A with both of the points and C with both of the points. Okay. So that's what I do. So I joined A with P, which is by this line. I join A by Q by this line. I join C by P by this line, and I join C by Q by this line. Okay. Now you need to see their intersection. So you can see that AQ intersects with CP at this point, and let's call that point to be R. Okay, and AQ intersects with CQ at this point. Let's call this point to be uh, yeah, AQ intersects with CQ at Q, and AP intersects with CP at P. We don't know the intersection of, yeah, and AP line intersect with CQ line at this point. Call this point to be T. Okay. Now we look at the diagonal of this uh, this quadrilateral. Okay, it has four. So now consider this quadrilateral P R Q T. PRQT. Okay, now consider this quadrilateral. So now in this quadrilateral, we have one diagonal which is PQ coming from BP. Um, so we need to look at the other diagonal. So other diagonal is RT. Now we need to see where this RT is gonna hit our line L. Okay, so RT intersection L will be our ACB, which is in this case 1/3. So this will be our harmonic conjugate. So it's an exercise type of question, uh, and it's a kind of revision also for you. Harmonic conjugate of a point, and in order to see why this harmonic conjugate of B with respect to AC only depends on point A and C, not on any other point P or Q. You need to go back to your lectures and see the proof of it. Okay, it's a beautiful proof. Okay, so I will not discuss this because in this question you need to um, yeah, I will not discuss because You need to find out, basically you need to find out this thing. So what is h 0 comma half, 0 comma 3 of half, basically harmonic conjugate of half with respect to 0 and 1 by 3. So this is your a, this is your c, and this is your b. Okay, now what you do, you take any point, let's say p, this is your point you have taken, and this is your q is a chooser. Now you need to find out the other diagonal and where it intersects. Okay, and how to do that is a simple way. If you think of if you think of some coordinate system over here, okay, then you are drawing a line which is bp. So you are choosing a point p. So let's choose the point which is, this is a point half comma 0. You choose a point, let's say some 1 comma 0, minus 1, 0 comma minus 1, sorry, not this will be some point, let's say um, half comma minus 1. Okay, I'm just choosing a random point. Okay, because it doesn't depend on the choice of your point p and q. And this point, and now you know the equation of line which is bp. So you know the equation of line of bp. You take a point q which is in this line. Okay, so you know you have b half comma 0, you have q half comma minus 1. So you know because of this equation of bp. And now once you know equation of bp, you choose a point q in bp. Correct. Now this point will lie on this. Obviously it needs to lie on that. So for example, this point will lie. Okay, so I take q to be this point. And now once you have q and you have coordinate of a, so you can talk about line which is aq. Okay, similarly line cq, and line like ap and cp. Okay, and now you need to find out the possible intersection of these lines. You will get the rest of the points like so ap, aq, cp, cq is missing, so cq will be this line, and it will intersect this line like this somewhere here. Okay, so this will be my point, and one of the diagonal will be this, so this will be my r and s. Yeah, so this will be r s p q p. Okay, so this will be my yeah, so this will be my triangle of concern. This will be my quadrilateral of concern. Okay, so one of the diagonal is already given. You need to find out the other diagonal. So for that you need to find out the coordinate of s. And once you know the coordinate of s, you can find out the equation. And also you need to find out coordinates of s and r. So r is nothing but the intersection of cr and sorry, r is the intersection of cq intersection with ap. So you have equation of both of the points, and now you have equation of both of the points. Now you need to find out the intersection which satisfy a point which satisfy both of the equation. So you know how to find out r, as well as you can find out s also, which is nothing but cp intersection with aq. Okay, so you will find out s also. And now once you have coordinates of s and r, you can find out the equation of sr. Okay, now once you have the equation of SR, you just need to put x equal to 0, because that's what this line, sorry, x by equal to 0, because that's what R is. Okay, that's what L is, in order to get the coordinate where it's going to intersect, which is actually 1 by 4. Uh, so yeah, so that's the procedure. Okay, okay, I stop at this moment. And if you have any question, you please ask me, because we only have 7 minutes left. Um, so any questions? Okay, so my another aim was to cover as many things as I can. Uh, so let me discuss one more problem with you until you guys are here, and we have, I think, 5 minutes left, and you don't have any other questions to ask. So we can discuss this question where we need to find out the value of x in the following diagram. Correct, in the following picture. So this in this question I will be using Papua's theorem, uh, Papu's theorem, uh, to find out the value of x. Okay. Now, can anyone tell me what's the statement of Papu's theorem, or just a hint? If so, basically, you need to find out x comma 0. You need to find out value of x. So, how you are gonna uh, use Papu's theorem to find out this?
Sir, Papu's theorem
Yeah.
said that these intersections of capital A, uh,
Yes.
I think B, and capital B small a, and
Yes. 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 Yes.
these intersections points are collinear.
Yeah. The intersection points are
Collinear.
collinear. Yeah. So that
So,
means these 3 points are collinear to each other. Correct. So I can draw a line joining these 3 points, something like this. Correct. So now you only need 2 points on a line to determine the equation of that line. Okay. So what will be the equation of this line? So let's say this line is L. So equation of L. So you have 1 comma 1 and 3 comma 2. So equation of line is y minus y naught equal to y naught minus y1, x naught minus x1, x minus x naught. Correct. So y minus, this will be 1 by 2. So x minus 1, 2y minus 2, it will be 2y. Okay, so this will be the equation of L. And now you need to put y is equal to 0, because L intersects x comma 0. So this will imply that putting y is equal to 0, so at y equal to 0, x is, what will be the x? Correct. So value of x is minus 1. Okay, so I stop here. Any question?
sir, we can use also here the area of triangle is equal to 0 for finding the x,
Yeah, that's also true. You can use area of triangle
because
formed by
these
these three
points,
edges.
yes,
Uh,
sir, by determinant like that.
but I think this is a simpler way. I find it simpler. If you find that simpler, you can use that also.
Okay, sir.
Yeah. Any questions? So in the next, like next week's session, I will start with uh, extended Euclidean space. Okay, and I will discuss a few questions from this extended Euclidean planes, and so it's a heads up for you guys. You can also do some exercises, and you can also come up with some question if you have any in particular about the extended Euclidean plane, and we will see. I will see you guys same day, Monday, same time, 7 to 8. You can use the same meeting link which is used today to join, and you will be able to find out the recording of today's session in the YouTube page. Okay.